Good day to you all, my dear class. Today I'm going to teach you about the testing techniques that you can see in all kinds of materials. So as you have already made some research on, let me show you what I've got about testing of materials. So testing of materials. Materials are tested for diverse purposes to determine the properties of the raw material, to check quality at intermediate stages in production processes, to check finished products also, and to aid some research process. Broadly, there are four types of tests. Mechanical methods, which are tests that the material's ability to resist tension, compression, impact, bending, twisting, and shearing, and its hardness and fatigue level. That is, its ability to withstand alternating mechanical loads without breaking. Second are the physical tests, which determine electrical conductivity, heat conductivity, cold resistance, and magnetic and other properties. The third one is the structural tests, which determine the macrostructure or structure visible to the naked eye, the microstructure also, which is visible through a microscope, and the crystalline structure determined primarily by X-rays. And the fourth testing method is the chemical test, which you can determine chemical composition and the ability to withstand chemical action, especially oxidation or corrosion. But in this class, we're going to talk about more about the mechanical methods and the structural tests, because we're not that about the physical and less about the chemical tests. The first one and the main principle testing technique is the tensile test or the tensile strength test. And this is to denote the resistance of a material to a tensile load applied actually to a specimen. It is very important to the tensile test to be considered as the standard dimensions and profiles that are going to be used for. This is that these are example of the specimens that you're going to put in here into the machine to make the test of the tensile strength. And what I was telling you about is that this specimen has to be put out in the machine to a certain load of the actual application that is going to be used for. The typical progress of the process of the tensile test can be seen next. And you need to have a special specimen of your material to run this test. Once you have the specimen made out of the material that you want to test, here's what you got to do. At the beginning of the test, you don't have any load. Second, you will have uniform elongation and reduction of cross-sectional area. And you can see here the elongation, because this is bigger than this one. The third is that you're going to continue the elongation until you reach a maximum load. The fourth is that the necking begins and the load begins to decrease. This is the neck or the necking, in which you start seeing that is going to break just a little bit. The fifth is the total fracture of the specimen, and the sixth is the final length that you can measure. And the same can be seen on a diagram, showing first here the elongation, the elastic elongation, then the uniform elongation until you can see the necking in this part of here, in which you break. You can see here the starting of the necking, and at this part you will see the break of the specimen. And in general, values of load and extension are of limited access since they apply on one particular size of the specimen, and it is more usual to plot the stress versus strain instead of force versus extension. So you will need to calculate the stress to obtain a plot like this, to plot stress against strain. So the stress is being calculated by the load or the force that you are applying to this specimen, divided into the area of the cross section, or the cross section area, and the strain is going to be equal to the extension, that is how much it was extend, this part, divided between the original length. That would be this one. This is the original length. And the percentage of elongation, which is an important property, will be calculated as the increase in length which would be this one, divided by the original length and multiplied by 100. Now, the ductility test. This has to do with the tensile strength and the bend test also. And we're going to see very briefly how can we measure some properties starting from this ductility. The percentage elongation that we saw on the last slide, as determined by the tensile test, is a measure of ductility, which can also be performed by a simple bend test. This is a bend test. And this is a closed bend test, in which the specimen is bent over on itself and flattened. As you can see, there is no allowance made for spring back, and the material is satisfactory if the test can be completed without the metal tearing or fracturing. So if you don't see any fracturing in here, you will have a metal that is approved for a closed bend test. The next type of testing in bending is the angle bend test. The material is bent over a former, and the nose radius of the former and the angle of bend are fixed by specification, in any specification that you needed. Again, no allowance is made for spring back. So if you have like a piece of metal in here, in which you can make this bend in this radius, and it doesn't deform or it doesn't break, it is approved for the bend test. And the last bending test is the 180 degree bend test. And this is a development of the angle bend test using a flat former as shown. Only the nose radius of the former is specified. Wait. Here it is. So this is the bend test, or the ductility test also. Now the compression test. Because of the presence of microscopic cracks, brittle materials are often weak in tension, as tensile stress tends to propagate those cracks, which are oriented perpendicular to the axis of tension. The tensile strengths they exhibit are low and usually vary from sample to sample. These same materials can never be quite strong in compression. Brittle materials are chiefly used in compression, where their strengths are much higher. These graphics are usually the same as the tensile test, in which you can see the stress versus the strain. So you have the stress versus the strain. You will have a load or a force into your material, and you're going to start to compress it until it breaks down. So mostly you will have the same types of plots, of graphics, of stress versus strain, in which at what point you will have the maximum compression limit, and then it's going to be breakdown. It's going to break. The toughness test, or the impact test, consists of striking a suitable specimen with a controlled blow and measuring the energy absorbed in bending or breaking the specimen. The energy value indicates the toughness of the material under test. This figure shows how a piece of carbon steel will bend. This will bend when you have an annealed thermal treatment before to this steel. So let's imagine that this is a rod of steel. You annealed it, and then you made a toughness test. So If it bends, then your annealed was correctly made. And in the other case, in which you have the same steel hardened and then tempered in the thermal treatment, if you do the toughness test, you will see it breaking or to see fracture it. There are several types of the impact test, and the mostly famous type is the ISOT test. In the ISOT test, a 10 millimeter square notched specimen is used. And it is preferred to use a specimen that have more than 1 or 2 and even 3 notched in the same specimen. The striker of the pendulum hits the specimen with a kinetic energy. This pendulum will hit this specimen, which is previously notched. It's going to hit it with a force with an energy of 162 joules at a velocity of 3.8 meters per second. So it is quite strong. And if this pendulum breaks this ISOT test, this will let you know in the friction pointer the scale at which how much energy does it take for the impact into your sample. Hardness has a variety of meanings. To the metals industry, it might be thought of as a resistant to permanent deformation. To a metallurgist, it means resistance to penetration. To the lubrication engineer, it means resistant to wear. To the design engineer, it is a measure of flow stress. To the mineralogist, it means resistant to scratching. And to the machinist, it means resistant to machining. Hardness is indicated in a variety of ways, as indicated by the names of the tests that follows. Micro hardness testing, indentation test, rebound principle, scratch hardness test, abrasion and erosion testing, flowing test, damping test, cutting test, electromagnetic test, and the last, ultrasonic test. But the ones that are most useful are the indentation tests, in which a ball, cone, or pyramid is forced into the surface of the metal being tested. The relationship of the load to the area or depth in the indentation is a measure of hardness, such in the Brinell, Knoop, Rockwell, and Vickers hardness test, in which, as you can see here in the image, you will have a diamond indenter and the measure of the area that was indented is a measure of the hardness of the material. And on the other hand, we have the structural tests. And some of these you may have been familiar with, such as the X-ray diffraction or the scanning electron microscopy or the transmission electron microscopy also. But these are going to be talked about in a different video. So thanks a lot. And remember that we have different types of testing for all of these materials. And it would be great if we would have this type of equipment in the UTM. Thank you and see you the next time.